Okay, wonderful. Well, thank you very much to the organizers for inviting me here to speak, given that I'm more of a mathematician. I think this might be of interest to some of you in the audience who are, Amplitudes practitioners who use maybe multiple polylogarithms, things like these to actually evaluate Feynman diagrams. I know some people don't use Feynman diagrams, but this is essentially an advertisement of some mathematical techniques that I'm developing in combination with some people in the Mass Camp ERC Synergy grant to essentially study Feynman integrals. So while I was walking here, I bumped into on the train Stefan, and we were philosophical, and I was explaining what this action that I'm going to describe is. So the point is, we're interested in studying periods, which are just very general integrals. And there's a more interesting structure you can consider that exists sort of on top of them, that permutes them. There's an algebraic group, this GAL-MOT, that acts on periods, to these general integrals, which should preserve all the algebraic relations amongst them. And this is purely hypothetical. It relies on some incredibly difficult conjectures in arithmetic. But what I'm going to show you is that you can, in a sense, take these periods, lift them to something, a sort of avatar of the period is called a motive. There's a very well-defined way to go back down, which is called a period map, from motives down to the periods that you actually care about. But upstairs, when you deal with motivic periods, there's a huge amount of structure. And in particular, we can make this group, which I'm going to describe, very well defined. So essentially sidestepping all of the conjectures that we have absolutely no clue how to solve. And maybe it's also worth saying, if we're in the physical situation where the periods actually have some interpretation as Feynman diagrams, Feynman integrals, just to be very clear, the group action I'm about to describe does not arise from some sort of Noether's theorem. There's no continuous symmetry of nature going on here. This is a Galois group I'm going to describe. And a Galois group, which you may have studied in a course in your undergraduate degree, it in some senses measures a level of ambiguity in solutions. So the familiar case, which was developed by Galois, was to do with roots of polynomial equations. In some sense, the group measures how much ambiguity there is in the solutions. So this case would be a permutation group. Could become very philosophical and wonder, where does this more physical Galois group, which acts on Feynman integrals, come from? And then, in that case, some ambiguity in how you're specifying your physical theory. So the fact that you're using Feynman diagrams in the first place comes from some, assumption that we can perturbatively solve our thing. Maybe you have a path integral involved, and there might be some ambiguity there in how you've defined your physical theory. So that was just a little note. There is no Noether's theorem going on here. This is a symmetry of basically arithmetic. So I'm going to describe sort of the baby version of a much more general theory that is being currently developed. I'm going to talk about a case which is very well studied, motivic periods of the fundamental group. So we're going to use motivic periods in this case to essentially derive these multiple polylogarithms. So there's a huge amount to discuss here, but as a toy model, all I need to have, the only necessary data, are some essentially Betti and Durham versions of a motivic fundamental group. And then there must be some sort of pairing between them as well. So there's a huge amount of relations here. But as a very loose definition, you could say that a motivic period is just this symbol, which has a lot of modulo all of these relations that you would expect integrals to have. So Stokes' theorem, bilinearity in both of these entries, change of variables. There's many relations between normal integrals that you'd expect to hold here. You can take this as some sort of toy definition. And our question is, can we construct a period map that goes from this incredibly abstract object back down to the numbers? The necessary tool is you need this isomorphism that compares the Betti and the Durham side. So you can think of this as the Betti would be like the domain of integration, and the Durham is the integrand. So some pairing between them, which usually is given by some sort of integration. Is there a way to construct this in this case? The motivic fundamental group pi1. The answer is these things called iterated integrals, which you may have come across before. Very generally, we write them as these symbols here, where there's some sort of time ordering implicitly involved in each of these omegas. So these omegas could be one forms. And you could pull it all the way back to some sort of simplex that has these like times. And this is explicitly what I mean by time ordering. So this is just some standard integral. And this is a well-known fact due to Chen, who sort of revolutionized the study of iterated integrals around 40 years after they were invented, is that there is some sort of iterated integration pairing between a Durham and a Betti side of this motive. So, okay, things are a bit complicated, what they are, but it's familiar in some senses. The pairing is also integration. It's a slight upgrade from the normal integration. And now we're iterating. So we have some time ordering as well. Okay, so we have some sort of way to compare these two sides. Now we can take the simplest case, which is possibly one of the richest ones, richest simple objects in maths, this P1 minus 3 points. We're going to consider the fundamental group of P1 minus 3 points. So we're really talking about the motivic version of it. So the generators of a fundamental group of P1 minus 3 points usually are just these loops that go around the punctures. So you'd have a puncture around 0, a puncture around 1, and then from that you could work out the puncture around infinity, or the loop around infinity. And there is a little bit of extra data that you need in order to make some of these integrals well defined. In particular, this business of tangential base points, there's a few ways of doing it, but there's essentially some extra information involved in this motivic fundamental group. That means that the integrals that you define based on these paths will be well defined. They will be finite. I'm going to give them some names here. They're image from this normal topological fundamental group, the loops around the punctures. Put them inside this more complicated object, which are so yeah, we'll say this this path from 0 to 1, we'll label it as this, and this path that loops around 0 will label it by this. The Durham side will have essentially we need these one forms that will insert into the iterated integral should be d log forms. This would be dx over x minus a. We'll label them by EA, where A will just be 0 or 1. Then we can define the motivic periods. So these will be the motivic versions, the sort of motivic avatar of, well, this one will be the motivic version of 2 pi I. And then this one will be the motivic version of a single zeta value. So these are some weird motivic algebraic looking objects. But we can always move back down to the world of normal periods, normal integrals, by taking this period map. And the period map, as I said, is this iterated integral. So this one should be obvious enough that you take the dx over x integrated around 0 and you get 2 pi I. This one is a calculation, but yeah, it turns out that we have a name for this, the period of this motive, and we call it zeta, the normal zeta function. And you can imagine playing the same game with many other, put many other words as your integrand. And then what you'll get is essentially multiple zeta values, so long as you're taking the path between 0 and 1. You can, of course, upgrade this a little bit. It would require some work. You need to work with a fundamental groupoid, where now your path doesn't really go from 0 to 1, but maybe starts at some x and ends at some y in P1. And then your path, if you were to integrate along that path, you would get some multiple polylogarithm. So there's a way of making this slightly more general. But the fundamental concept is here. We have a motivic version of 2 pi I and a motivic multiple zeta value. Okay. Now let's think a bit about this Galois group that I claimed we could define meaningfully. So the history of this is very interesting. There was always this notion, going back to Grothendieck, he wrote down a sort of a program for investigating this absolute Galois group, which is this object here on the left-hand side. He said you can study this by really just considering its image inside some sort of completed fundamental group of P1 minus 3 points. More generally, he said, you would actually need to study how this thing acts on, how this absolute Galois group acts on the fundamental group of MGN, the moduli space of curves. But there would be essentially sufficient data in the fundamental group, complete fundamental group, to tell you exactly what the absolute Galois group is, what its generators are. It's an incredibly complicated object, but you can derive enough information to specify it completely just by studying how it acts on some very simple things. Okay, so fast forward, and you might want to make this whole construction motivic. It turns out that this sort of conjecture can be made meaningful if we're in the land of motives. So this is conjecture, a very hard conjecture. This is fact. So there is a motivic Galois group acting faithfully on the motivic fundamental group, at least the Durham realization of it. Choose which realization you want, the Betty one also.
Could you say quickly or repeat what is the absolute Galois group, this Gal Q bar?
So if you're familiar with how the Galois group acts on, for example, roots of polynomial equations, it's some sort of permutation group. Yeah. Okay. You could consider collecting all of these permutation groups together. There's a way of doing this, to study essentially how the group acts on every algebraic number at once. So this is what the Q bar is.
Okay.
Q bar is not like the reals. Yeah.
Completion of.
It's the algebraic completion of Q. So you write down any equation with coefficients in Q.
Yeah, right. Yeah, sure.
So for example, the square root of 2 lives in there. You know? So it'll tell you how every algebraic number moves around each other. So incredibly complicated object. Every solution of an algebraic equation at once. And somehow there's enough data in this very simple object to specify every single generator of this group. So it's surprising, and it may be false still, but at least in this motivic land, absolutely true. So rather than write down the action, it actually turns out it's much easier to write down a co-action, which is, okay, this is just a formal manipulation. You take some sort of group action that looks like this, acting on motivic periods. You dualize it, you reverse the arrows, and now you're considering functions on the Galois group. So there's this reversal you need to use. I don't know if you need me to do this. As an example of how this works, using the motives that I described earlier, we have this 2 pi I motive. The action of the motivic Galois group on this one is simply by scaling. So you scale it as some rational number. It's a calculation. Meanwhile, if you act by this motivic Galois group on the motivic zeta that I defined, then there is some sort of affine transformation of motivic zeta. And this is crucial. It's the same lambda that you had when you acted on the 2 pi I. Yeah, so in this sense, also some sort of absolute Galois group. It's acting on everything at once. Okay, so this gives you some very interesting non-trivial constraints between different motives. Okay, and then I've written, for convenience sake, how this would be written in the coaction world as well. A simple example.
How does the coaction look like? So if I understand, when you say motivic, I can also consider like functions there, or like the symbol, like the letters E, right? So how does the coproduct? How should I think the coaction, sorry, on these objects, like on the functions, for example?
Yeah.
Is there a simple way to?
Well, this is the prototype formula. This is a sort of unconditional formula for how a motivic coaction works. When you take a basis of your Duran, pi 1 in this case, and then this is an abstract formula for any coaction. So
Let's follow that. Okay.
any motivic coaction will look like this. Not even in the pi 1 case, but there's more complicated cases. Okay, so this is a formula that was figured out by Brown and Goncharov for the general coaction formula. So this looks quite complicated. Okay, you take coaction of this motive. We call it the multiple zeta value motive. It splits into this weird product over some sort of partition of its letters. But you can have this simple image in mind when you want to calculate this. So you draw every single possible chord diagram in blue like this. So you split up your word in this strange partition, sum over every possible one of these chords, and then you assign so the left side and the right side by which of the letters are the endpoints of the chords. So this has been proven. Okay, this is all classical. Was figured out around between 20 and 10 years ago. More interesting question you can ask now if you want to make this useful for yourselves as physicists. But usually our integrals are absolutely not convergent under any conditions. So regularization is very important. A conjecture, essentially due to Abro, Brito, Duorgadi, and Matthew, is that in fact you can use dimensional regularization and coaction at the same time. So this leads to a need to define these things called Mellin motives, where you're now inserting some sort of dimensional regularization parameter inside your motive. So the corresponding period is the Mellin transform of the period. F is just an algebraic function. So the problem with this is now you're making your thing inside here, your integrand, multi-valued. And the previous things I've described are not equipped to deal with the multi-valued case. So the question is, can we actually figure out a coaction, maybe using some previous knowledge that we had about the other coaction in the single valued case, now that we want to Taylor expand in our dimensional regularization parameter. So as an example of,
sorry.
Go ahead.
Yeah. What do you mean before it was multi-valued? Like the polylogs aren't.
And now you can use the arrows. Should be able to.
But aren't the polylogs multi-valued? Maybe I don't understand.
They're multi-valued if you have some sort of parameter in the domain. So if sigma starts and ends at say 0 and z, you'll get a multi-poly logarithm
right.
of z.
Okay, yeah, sure.
But now I'm talking about making the integrand multi-valued.
Okay.
This is where the coaction will be acting essentially on the Duran side. So this is where it's important. But yeah, very good question. Thank you. Okay. So as a very quick example before lunch of where this might work, I'll give you a clue of what to do, is you take the beta function, which has these sort of twists inside the integrand. There's a very famous formula for how to work out the Taylor expansion of this thing that involves zeta values. So you might hope, aha, we can create some sort of motivic beta function simply by replacing every occurrence of zeta with a motivic zeta. You can define this thing, and now it sits in some ring, some power series ring of motivic periods. It's a purely formal manipulation, but then what you do is you just simply apply the previous coaction I defined for zetas, these motivic zetas, and you get something that's also quite interesting. You get some sort of formula for the coaction of motivic beta, which I won't go into, but it has some interesting properties not present in the previous case I was talking about. In particular, there's some sort of factorization of where the power series sits. So currently what I'm trying to do is systematize this lifting of the previous well-defined coaction, which works on the case of P1 minus 2 points. And we construct various Mellin motives, such as the beta one, and get an explicit coaction formula with some sort of diagram that looks the same as I had in the previous slide with this chord construction. And the answer is yes, you can. But I think that's all we have time for today. Here's a Mellin motive. Thank you.
Thank you very much. I guess we probably have time for a few questions before lunch.
Yeah. Hi, James. Yeah.
This is probably related to the comments that you were just making. But the fact that you can by the coaction expansion, so you do something. So I mean, having in mind dimension,
Yeah.
and your coaction to the coefficients that you see in the
Yeah.
fact that that is action on original. That's something that you construct the coaction, or is it you get that from somewhere else and then find that it's a pattern?
So this is an excellent question. Thank you. Essentially, what's going on is there's two things. You could, by pure thought, create some theory of Mellin motives that doesn't rely on this power series expansion thing, and write a coaction formula for that. Some sort of unconditional coaction, the way that I wrote in some previous slide. This is now formalized as a theorem by Brown, Tapskovich, Frezan, and Dupont. But you could equally have done the alternative route where you use your previous coaction formula and just try and lift it, applied by brute force. Power series expand, because you know you want to do this for physical applications, and then apply coaction term by term. It's going to mix everything up in some horrible way. Then you try and recombine it, rearrange your power series in a way that leaves you with a Mellin motive at the end as well, on left side and right. And it turns out that, like, from the calculations I've been doing, you can in fact do this. So you can always recombine to create a Mellin motive from the brute force, expand, apply, recombine. So this is something which, yeah, I guess will be coming out in the next year. Yeah, thank you though.
Okay, well, if there are no other questions, I guess we can break for lunch there. So thank you again.
Thanks.